Now on to the third section in the parameter estimation and tracking 2 lecture set. Now we're going to discuss phase comparison monopulse and the next items on our outline here. Phase comparison monopulse is a method of finding out exactly where a target is within the beam width by having 2 separate antennas radiating in the same direction. It's also known as an interferometer radar. And what we do is when we have a target at an angle theta off the bore site, we measure the difference in phase between the arrival at this antenna and this antenna of a target. And the phase difference of the signals received from the 2 antennas is just the delta phase is equal to 2 pi times d, the distance between the 2 antennas, and divided by lambda times the sine of the angle. So you can see that if you measure directly the phase, you'll know exactly what theta is. And so that's how phase comparison monopulse is constructed. Comparing the 2 methods of amplitude comparison monopulse and phase comparison monopulse. With amplitude comparison monopulse, we have a common phase center, and the beams are squinted away from the central axis of the bore site of the one antenna. And the target produces a signal with the same phase but with different amplitudes. The on-axis amplitudes are equal. Phase comparison monopulse, the beams are parallel and identical, and the lateral displacement of the phase center has to be much greater than the wavelength, and the target produces a signal with the same amplitude but with different phase. The on-axis phases are equal, and with these type of phase comparison, with phase comparison monopulse, grating lobes and high side lobes can be a problem. You can do angle estimation with array antennas with this phase comparison monopulse technique. If this is the direction of propagation, an angle theta off the bore site, and this is the wave front of the beam going out in the near field, and here are the received phase fronts. The received signal varies in phase across the array when it's out at an angle, and the phase rate of change is related to the direction of propagation, and estimating the phase rate of change indicates the direction of propagation. You can measure the angle of arrival and the direction of arrival. Now let's look at another method, sequential lobing. Here we have an angle tracking technique where you share a single antenna beam to obtain the angle measurement in a sequential manner. If here is the bore site between the 2 beams, we send out beam 1, and then we send out beam 2, where V1 is the voltage from the upper beam and V2 is the voltage from the lower beam, and this dashed line is the antenna pointed at the target. Now, if V1 is greater than V2, the antenna is pointing too high. If V1 minus V2 is less than 0, the antenna is pointing too low. And if V1 minus V2 is greater than 0, the antenna is pointing too high. And if they're equal, the volt V1 and V2, the antenna is pointed on the target. Let's look at sequential lobing in another way. Here we have a target location in the black solid line, And this is the switching axis where we switch back and forth from one beam to the other. And for this target, we'll receive for beam 2, which is the red dashed lines, this will be the center of beam 2, and we'll get a higher amplitude. And the center of beam 1 over here. Now, what we'll do when we have if this is the switching axis, we'll have at position 1, the target will have a lower value, and when it's in the target position is on beam 2, we'll have a higher position. And so as you go back and forth, you see you'll get different amplitudes because we're looking at different places in the gain pattern of the antenna. The difference in echoes between the two switched beams is a measure of the displacement of the target from the switching axis. The beam is usually larger, with the larger signal is closer to the target. You can see that the target position is here, and it's closer than beam 1's position from the target position. And a control loop is used to redirect the beam location to equalize the beam responses, and that would put the target position right at the center of the two beams. The two beams would be one on top of the other and centered on the target. When the echo signals of the two beams are equal, as I just said, the target is on axis. Now let's look at conical scan in tracking systems. This is a system where we have a single dish antenna, and we have a gimbal on the feed, which rotates the beam about a rotation axis. And there's an angle between the axis of rotation of the beam and the axis of the antenna beam, and that's called the squint angle. That angle right up there. In blue, that's the axis of the beam, and the rotation axis is somewhat off axis. And what you would do is send out pulses, many pulses per rotation of the beam. So here we would see the beam at this location. Typically there'd be 8 beam positions per scan in a typical conical scan pattern, and then here, and then here, and then here. And they will all have different amplitudes. Because of the rotation of the squinted beam, the target's offset from the rotation axis. The amplitude of the echo signal will be modulated at a frequency equal to the beam rotation. Now let's see what that looks like right here. We have these different pulses, and here's the received signal amplitude, and this is its time. And this is the envelope of the received pulses. And what we're looking at is the received pulse train with the conical scan modulation, and the amplitude of the modulation, this amplitude peak to valley, is proportional to the angular distance between the target direction and the rotation axis. It's the beam displacement from being on axis. If there were no modulation, there'd be no squinting of the beam. The phase of the modulation relative to the scanning beam position indicates the direction information. It tells you the error information. Now here is a block diagram of how such a radar would be implemented. And these are typically used in range instrumentation systems. We're just going to neglect the transmitter. The signal comes back, sends out those 8 pulses as we're looking, and the beam is going around. sending out at least 8 pulses per rotation, come back through the duplexer. There's no signal going to the transmitter through the receiver. And then you'd have a range gate, because these are typically used for single target trackers. And the antenna, the error in the signal would go into an elevation angle error detector for elevation and for azimuth. And then each of these would go into an elevation and an azimuth servo amplifier, and they would have a reference generator that would reference the frequency of the scanning, and that would feed into this error detector so you'd know the sign of which way to go. And then that servo amplifier, after it gets its output from the error detector, would amplify the signal and then tell the elevation servo motor which way to point in elevation and also in azimuth in order to get the target right at the center of the beam. And this part of the conical scan system would be in the pedestal, right up in here. Now, when we do beam splitting, typically when we have one pulse with a conical scan and one pulse with a monopulse scan, I first just want to concentrate on the monopulse, and then for one pulse. A typical, because that's typically what is used. A typical detection thresholds of about 13 dB, the resolution cell can be approximately split by a factor of 10 to 1. And you remember the 0.7 times the size of the beam divided by the square root of the signal to noise ratio. Okay? And here's that 13 dB, and here is a tenth of a beam width. It's the error divided by the beam width. And you can see that the error goes up somewhat with a conical scan. As we discussed earlier, the conical scan has more error in it than a monopulse scan. And if we use more pulses, we coherently integrate 4 pulses, we'll get a little bit more signal to noise ratio, and that will give us, these are signal to noise ratios per pulse. You get a little bit better accuracy if you had 4 pulses that you were integrating instead of just 1. Now, with track while scan antennas, we have a different issue. Here's a picture of a fellow standing on an ASR 9 antenna, and you notice it has 2 feeds. One feed is used to broadcast a beam, to transmit a beam at a low elevation angle. It's very wide. And another one to transmit one higher. So it covers elevation in great variance of elevation angle. It's a 2D scanning antenna. That's because you can see that it has a much shorter aperture size and elevation vertically, and a much longer one in the horizontal direction. These particular antennas also have shaped beams, if you remember back to the antenna lectures, so that they fill up quite readily a cosecant squared pattern. So let's just take this, and power as a function of angle as the antenna pattern, and here's the location of the target. Now, as we scan by the target, the antenna will be at different, if we send out the pulses fast enough, the antenna will be over here, over to the left. The center of the antenna will be over to left, and the amplitude that the target will see is this point in the gain pattern. And then as it scans more towards the target, it'll you'll have detections here and here and here and here. There'll be a pattern of detections which essentially measure the gain pattern of the antenna. And here you can see in shading the motion of the antenna as it scans by with a mechanically rotating antenna as it scans by a target. So what we've got is an output of a scan angle with detections in a number of different pulses. And we'd be setting, typically with these antennas, they have sufficient signal-to-noise ratio. We set a detection threshold down here, and we'll have a bunch of these. And there are a number of different ways that you can measure the angle accuracy within the beam width with a trackwell scan antenna. We can fit the return angle data from the different angles to the known antenna pattern. Or we can use the highest amplitude return as the measured angle amplitude location. And they will give us a very quite good, and of course it depends on the signal to ratio of the target, a quite good accuracy on the angle estimate of the azimuth pattern. Now, angle estimation with array antennas is well suited to monopulse tracking. With amplitude comparison monopulse, the radiating elements can be combined in 3 different ways to make a sum, a difference, and an elevation difference pattern, and go through the standard method of making of measuring monopulse. You can also do phase comparison monopulse by using the top and bottom half of the antenna for elevation and the right and left half of the array for monopulse. With lens antennas like the multiple object tracking radar, the MPQ-39, that would use amplitude monopulse because this is essentially a horn which I showed you earlier, a horn which directs energy out to a set of phase shifters along this face. I think there are about 4,000 or 5,000. I think 4,192. Don't count me on that, though. And those different phase shifts move the beams at different locations. But at the horn, there is a 4-port feed horn, which would be the same as for a dish reflector. Now we'll move on to range tracking. In earlier radars, before we dealt with A to D converters, the echo pulse would come back and we'd have a gating system set up so that we'd have a gate that would be divided into 2 gates, an early gate and a late gate. And this would move across till you had an echo pulse. This would be the noise level. And then what you do is you take the early gate section, you'd gate this echo pulse, and there's a certain amount of energy that would be in the early gate, and a certain amount in the late gate, and then you'd move the gate till there was an equal amount in each, and take a difference signal between the early and late gate, and you can make an estimate of where within the pulse the range signal was. So let's go over that again, just to reiterate. 2 gates are generated, one's early, one's late. In this example of the signal in the early gate is less than that in the late gate. The signals of the 2 are subtracted to produce a difference error signal. The signal of the difference indicates the direction of the 2 gates have to be moved in order to have the pair exactly straddle the echo pulse, and the amplitude of the difference determines how far the pair of gates are from the centroid. Okay, now single target tracking antennas that track an angle can also be configured to track other targets within the beam. And these are useful for radars with moderate to wide beam widths and favorable geometry is helpful. And by that I mean there are other targets that are of interest that you might want to track that are nearby the main target in tracks. The TradeX radar at Kwajalein, for one, has and several other radars have multi-target trackers implemented. The primary target is kept on bore site with standard monopulse tracker, and up to 10 other in the radar's beam width are tracked in range with standard measures. Some other radars track in Doppler and in range along with tracking an angle. And now let's look at servo mechanisms. We've sort of gone over them lightly. The automatic tracking of a target, an angle, employs, as we've seen, a servo system which takes an error signal and uses that to maintain the pointing of the antenna in the direction of the target. The servo system will have a lag in the tracking that results in an error. It'll overstretch and then it will come back. And the lag error depends on the target trajectory. The lag error will settle down to little or nothing if the target's on a straight line. But if it's taking a gradual turn or rapid maneuvers, there can be a significant lag error. And we'll see later on where trackers will veer off before they get back on. What's known as a Type 2 servo system is often used in a tracking radar. There's no steady state error when the target has constant velocity, and it's known as a zero velocity error system. The effective velocity and acceleration in the servo system can be described by the frequency response of the tracking loop. And most electrical engineering students go down to this when they'll take a course, many of them will, in elementary control theory, and they'll learn about servo systems in that. But this is enough to just show you on the big picture. Now, the servo systems have a bandwidth. The tracking bandwidth of the servo system is that of a low-pass filter. If you want the filter to have a bandwidth that's low, to minimize the effect of noise or jitter, and reject unwanted signal components such as jet engine modulation or conical scan frequencies. So you want it to just pass low. It should be wide enough, though, to follow rapid changes in the velocity of the vehicle carrying the radar. The choice of the servo bandwidth is usually a compromise between the sensitivity and the maneuvering of the target, and the tracking bandwidth may be variable or adaptive. So this is a whole game, and not a game, but a lot of complex techniques that you can get into. For far ranges, angle rates low, and low signal-to-noise ratio, you'll have a very narrow bandwidth. At short ranges, the angle rates can be large and you want a wide bandwidth, and at shorter ranges, glint can be an issue to begin with. Now here's a graph of the resonant frequencies of different radars. Haystack is a huge radar. You've seen pictures of before. It's, a 120-foot dish. The FPS 16. It's several meters in diameter. And the APG-66 is a small fighter radar. And you see that for the antenna dish size, when they get very large, the resonant servo frequencies are low, and the resonant servo frequencies are high for small antennas. The tracking bandwidth of a mechanical tracker should be small compared to the lowest natural frequency of the antenna and its structural foundation. And this prevents the antenna from oscillating at its resonant frequency. Now, in summary, what we've done is we've had a detailed description of different radar observables, and their estimation was presented. The observables, range, azimuth, and Doppler velocity. We've looked at cross-section observables and their estimation in a previous lecture, and we added some more information in this lecture. And resolution, precision, and accuracy were discussed. And then we looked at detail of a number of different target tracking, angle tracking techniques, amplitude, monopulse, phase comparison monopulse, sequential lobing, and conical scanning, and range tracking techniques were also presented. And this is a summary for part 1. The references from this is for the problems are these problems in Chapter 4 of Reference 1, which is Skolnick's Introduction to Radar. And these are the references of the texts that I've used in putting together this lecture. And I'd like to thank, for some of the material and ideas, Catherine Rink and certainly Eli Bruckner, who has a great book out on tracking. Let's see if I've referenced it. Oh my gosh, I haven't referenced it. I'm sure in the next lecture in tracking, I reference Eli's book on tracking. And I'll point that out to you. And now we're going to go on to part 2, which is actually a second lecture, lecture 16, where we're going to discuss multiple target tracking